Here we're going to work on an example on the linear least square regression. You can see the question on the screen. I would suggest that you would pause the video and read the example for like a few minutes, 2-3 minutes, and then try to work on part A of it. Then come back and see that how we're gonna do that. So in the example, it says that we have an article, and in the article there are data. We have some data that is presented, and the data there, it's on X and Y. X is the representing compressive strength and Y is the permeability. So I wrote down the data that we have here, all of the data that you can see in the example, and we have 14 data points, 14 observation, and then the sigma of each of them, right? Assume that the two variables are related according to the simple linear regression model. Awesome. So it says that we can use the simple linear regression. And when we say simple, it's like that we have just one independent variable or one regressor in our regression model. So this is the regression model that we have. I wrote it down here in advance just to save some time. So it's y is equal to a0 plus a1x plus e. So y is the permeability, x is the strength, and then e is our residual. So I'm going to write down this one here. It's our residual. Okay, so in the part A, it says that calculate the least square estimates of the slope and intercept. So we want to find out our intercept, which is A0, and also a slope, which is A1. For the equation that we have, this is part A. So here is part A. We have, from the equations, we have A1 is equal to n sigma xi yi minus sigma xi, should be times yi, yes, sigma yi, and then divided by, in denominator, we have n sigma xi power 2 minus sigma xi, whole of it, like the whole sigma xi power 2. So with this one, we just replace the numbers. So n is 14, right? Sigma xi by I, we have it here. So it is times 1697.8 minus sigma xi and sigma yi. So it's going to be 43 times 572 divided by n again, sigma xi power 2, which is 157.42 minus sigma xi 43 over 2. So when we do this calculation, our answer is going to be minus 2.330. So here we found out the slope. The slope is minus 2, so it's like going down. From here, then we can say that our correlation factor is less than 0, is between minus 1 and 0, but we are going to work on that. So the slope is negative, and then we want to find out A0. With the A0, we have for this y bar is equal to sigma yi divided by n minus A1. We found it from here. And for xi, we are going to have it like sigma xi divided by n. So we're going to replace the number like sigma yi. The value of it is 572 divided by 14 minus this negative 2.330 times 43 divided by 14 again, and the final answer for this is 48.013. So we found that A0 and A1, so we can say here our estimate for our model. For the estimate, we use hat sign in statistics. So estimate for our model is going to be equal to the A0, which is 48.013 plus A1 is negative 2.33, so I can write down negative 2.33, and then I have my x. So this one is my regression model. I call this model that you see here as my regression model. This was part A. Part B says that use the equation of the fitted line or the regression model to predict what y would be observed when the x is equal to 4.3. So in part B, it says that if my x is equal to 4.3, find out an estimation for y. So find out what's going to be my y estimation. So if we have the equation here, 48.013 minus 2.33, x is 4.3. So the value is 37.99. So if x is equal to 4.3, our permeability is going to be 37.99. Okay. Okay. So for part C, it says that suppose that the observed value of permeability at x equal to 33.7 is y equal to 46.1. So part C, it says that from our observation, when our x is equal to 3.7, our y is equal to 46.1. So this is not the predicted value. This is just our observation, right? So with this observation, and at the when we continue reading this, I calculate the value of the corresponding residual. So we are looking for the residual. Residual is equal to the whatever we have as an observed value minus the predicted value. So here I'm going to write down E is equal, this is the residual, right? Residual is equal to the observed value minus, and this is going to be my predicted value, so minus predicted value. E is equal to y minus A0 minus A1 x. So what's my y here? 46.1 minus, what's the A0? It's 48.013 minus A1, which is 2.33. So A1 is minus 2.33. When we have minus of that, it's going to be plus. And then our x is 3.7. So when we deduct these two, the value that we find out is going to be, for the residual, 6.71. So this is going to be my value for the residual here. In part D, it says that calculate the correlation coefficient to quantify the goodness of it. Okay, so for the correlation coefficient, which we show it by R. In some books, you can see that they show it by rho as well. So here, some books show it by rho. Both of them are acceptable. So with the correlation coefficient, we have this equation for it, like the same equations that we have for these ones, so we can find out the equation for the correlation coefficient as well. But let's see what's the concept of it. Correlation coefficient can be between -1 and 1. So when the correlation coefficient of something is 1, in fact it means that the two variables that we have, like x and y, they're highly correlated. So when they are highly correlated, it means that we can have a line to connect them together, like to predict the value of that. So for example, look at here. If I have something like this, like these are my data points. If my data points, they were like this, right? And then I would have a line, let's say the prediction line like this. So with this one, probably the R or the correlation coefficient is close to 1. So they are hardly correlated. For example, you can say that for the correlation coefficient, if let's say the oil price and the airplane tickets, right? Let's say if the oil price goes up, the airplane ticket is going to go up as well. So they are correlated in both of them in the positive way. So R is close to 1. In some cases, they are highly correlated, but if one of them goes up, the other one goes down. For example, in industrial application, we always say that, okay, so if we have if the consumption of fossil fuel goes up, right, and the consumption of the fossil fuel goes up, oh, this is another example of the positive one. The greenhouse gases is going to go up as well. Another thing that we can say, like the one it goes up and the other one goes down. Most of the time, the things that they have trade-off together, so we would with each other. So we would say that they are correlated, highly correlated, but in a negative way. So, for example, if the temperature outside goes down, outside the house, let's say in winter. So when the temperature goes down, the consumption of the gas inside our homes, it goes up. So we are going to use more gas, or we are going to use more electricity for heating purposes. So we need to generate more heat when the temperature goes down. So in that case, the way that we would show it is like that. They are correlated, look at here, right? But it's like they're correlated like this. So with this one, we would say R is close to -1. Okay? And sometimes they're not correlated. It's like, for example, look at here. If I have something like this, and my line be something like this, we would say that the correlation factor is 0. So it means that they are not correlated. So now let's go back to our question. It says that find out the correlation factor for this one. So what are we going to do? We are going to put all of these numbers, like N14, sigma xi by I minus sigma xi times x sigma y. And then on the bottom, I have the square root of the n times sigma xi power 2 minus sigma xi. So we're going to replace all of the numbers here. And when we did that, the final value is going to be minus 0.9237. So it's like negative 92%. So it's like close to 1, but it's negative. So it means that our variables, these two, they are correlated. They are highly correlated, but in a negative way. So if one of them goes up, the other one goes down. Even when you look at the equation here, you can see the slope is negative. So the line that I'm going to have for this one is going to be similar to this line, right? So this is the correlation factor. In this example, we worked on the how can we use the least square estimate for finding out our regression model, and then we worked on the correlation factors, like coefficients, and also the residual of it.